Today, I'll be connecting some papers in when it comes to reasoning models, specifically the failures. So, uh, so in the last few year, in the last year, majorly, and this 2025, there's been a big interest in RL for LLMs generally, and this effectiveness comes from like when using LLMs, it comes from two specific parts to it. So we can now model tasks in the form of environments, or we can model them with rewards. So just say you have a data set. Now you can start like using your LLMs to start generating some outputs for those tasks, and then you can reward it based on if it's correct, if it's wrong. Uh, for example, here, this is from DeepSeek R1. DeepSeek R1 rewarded its model based on accuracy rewards. So, given like if it was lead code or if it was math, uh, they gave accuracy rewards, and they had this format reward, which was basically they were asking the model to, they were enforcing the model to give their outputs in think or yeah, these think brackets. And it's been very, very effective for verifiable tasks, and performance on non-verifiable tasks depends on one, it depends on how well you can reward the model. You can model the reward. I'll go to an example very soon. And the second is what benchmark you're trying to hill climb on. So basically, one perspective that I will take in this talk mostly is that benchmarks have dominated how we think about these things. And depending on the benchmark that we want to hill climb, the way we model the task, the way we reward the models, all of this has changed. So, for example, like when it comes to verifiable rewards, the most simple one says math, wherever you are given like a simple prompt, and you're just asking the model to like output what the answer is, and then you're just using a symbolic equivalence checker to see if the output that the model gave is the right one. For coding, it's based on how many tests it passes. For short form QA, it's basically like text matching. For instruction following, we've been using RLHF, or like, yeah, you can even use an LLM as a judge. It's basically preference modeling that has been like mostly the status quo for that. One example for non-verifiable rewards is basically this paper, which is learning to reason for factuality. And this is for long form factuality. This is not like simple Q&A, which is simple, like you can just text match and say, okay, this is done. In this, the way they've done this, so they have to do like they would reward long form factuality, and the reward design for this slightly looks different than otherwise. So they have two parts to this reward that they've given the model. One is this very score, which has factuality precision, and it also has detail level. Basically, what this is just saying how correct is the model, given all the details, given all the things that it is saying in a long form answer, and what's the detail level, like how much detail is it able to give. At the same point, they also have answer relevance, like given a question, how relevant is the answer that it has given to the question itself. Combining this, ultimately they have this reward for factuality, long form factuality, and this like mostly works. So the way they evaluate this in this paper is they use health bench, and they have these five criterias. The base model that they've used in this paper is 20.57b, and these are the other kinds of rewards that they've tried, like Likert score, which is just 1 to 5, and then there's this like their rubrics as reward, which is basically the one that I just showed. And they say that like the overall score is generally better than the base model, and at the same time, not only is it better, it's better on every front, which is communication quality, accuracy, and all these other things that they care about. One more thing that they show is that while this is not a major bump, when trained for health bench, they found that they could have some rewards like which transferred over to GPQA Diamond as well. So yeah, so that was basically me telling you about why RL has become effective. because, well, you can like model both verifiable tasks and non-verifiable tasks, and that's become very, very interesting because depending on like it does not really matter what field you're from, as long as you can model it in a way that you can like interact with an LLM. It's something that has worked. We've seen some things from chemistry, for physics, even for creativity, for chess, for other games, and all of this. And that has become a really, really popular like source of engagement, and even like one, you design the benchmark, two, you train these models to get better performance on these tasks. Okay, so one thing that has also become like at the same time, uh, so there are some criticisms for RLVR, that is, which is the major paradigm of doing RL, which is like verifiable rewards, uh, which is the major paradigm of doing RL within the LLM field. And the criticisms mostly are like, so in this case, the criticism in this paper, uh, yeah, just a side note here. For most of this talk, what I'm trying to do is all these papers in this talk will mostly could have their own like hour-long talks and we could dive deep into them. But what I'm trying to do here is connect some ideas and give you a broader perspective on what's happened, and like yeah, just give you a overall big picture and see where we fall at. Okay, so having said that, resuming the talk. So in this paper, what this basically says is RLVR is not really encouraging the model to learn new patterns or discovery of like new thinking modes. What it's doing is just making the model sure of something that it already knows. That is what it like. That is the major idea takeaways from this paper. And the way they do this is they have this experimental setup where for maths, code generation, visual reasoning, and deep analysis, wherein they're using an RL framework using these different models, and they have this algorithm and they have these benchmarks. What they ultimately say is on the left side, pass at one here is basically the pass at one that you can see from these, like when this model is trained on this specific algorithm. And pass at 256 is what you like. This is just the base model. Pass at 256 self-explanatory here. You're just sampling the model 256 times. So what they say is that what RLV is basically doing is it's just making the model uh, it's just increasing the model's surety of the answers that are already existing within the base model. And the way they show this is as the pass at k increases, what it does is, as you can see, Quen 2.57b, like it has about 67.2 here. And when you look at reinforce or all of these other algorithms, the path at 256 is very similar to the base model, which has not been trained on anything else. It's just the base model. So the path at 256 matches. And they show this for different tasks. This is not just the case for math. As I said, they show this for code generation, visual reasoning. So what they say basically is that it's just making RLVR is just making a model more sample efficient, and it's reducing the scope of reasoning capacity. And that is the major like criticism, and that is why this paper became really popular. And people started looking at what exactly causes this. One thing to note here, generally in these models, is that they've always like, or most of these RLVR experiments have not happened in really, really bigger models, like 70 billion parameter plus models. If you read the original R1 paper, you might see that when they talk about some exploration capabilities in their models, they're really talking about it in models which are bigger than about 32 billion parameters, and that is where they start seeing some shift. That's not really a criticism, but just something to keep in mind that most of these experiments are done in this compute like bound space. One other paper that came out this year is Spurious Rewards, Rethinking Training Signals in RLVR. What this paper does is basically, so they have like these, like on the top right corner, you can see that there's like 7 types of rewards that they're considering. You have before RL, then you have the standard ground truth reward. You have this majority vote, which is the most common label that you can take when you have 64 rollouts. Then you have this one shot RL and format reward. Format reward is just like sole format reward. You're not giving it a correctness reward in that. And then you have these spurious rewards, which is incorrect label. You're not giving it the right label, or just random reward. What they find in this paper is when Quen 2.5b was trained on incorrect labels or random rewards, even then they saw some gains from they saw some gains from these models, and that is what you see on the in the left, like Quen 2.5, both Quen 2.5 math and Quen 2.57b, both of them have like even when given incorrect labels and random rewards, they see that there's gains. This is not the case in Olmo 27b, and this is not really the case in Llama 3.1 as well. When you look at incorrect label, it's not really much. This is some level of chart crime. Not no comments on that, but yeah. So there's not really much rewards here. You could take this as a criticism both for RLVR, or you could take this as a criticism for the model itself, that maybe the models were trained on too much, and any sort of like rewarding just gets the latent behavior that it has taught, that's been taught to the model, come out. Or yeah, so maybe, or there's some contamination. This paper is not really looking at all of that stuff, just in independent of all of those things. When trained on these kinds of spurious rewards, it still works for some models. So follow-up work on that specific aspect is this heuristic considered harmful. So this blog mostly was looking at this paper, spurious rewards, and what this blog basically says is if you're doing true policy gradient, and if you're just using random rewards, it should, like, this policy gradient should mostly cancel out. Sometimes it will promote right behavior, sometimes it will promote incorrect behavior. But as you go over time, the accuracy of the model should stay stable and it should not really promote anything. So for this, what they basically do is they consider two types of algorithm families, which is one is the natural policy gradient and the second is heuristic policy gradients. Basically, what heuristic here means is either you are using clipping or you are using some normalization term, and PPO, GRPO family, like these algorithms are basically in that space, while RLLOO, which is leave one out, and Rebel are basically like policy gradient algorithms which don't do that. What they basically say is, as you can see the graph here, as the model is trained for Math 500, over time, both Rebel and RLOO, they basically, the policy remains the same. Even like this is specifically when given random rewards, but when it's like trained with GRPO or PPO, the model suddenly starts, like the accuracy suddenly starts increasing. They mostly attribute this to the fact that this sort of heuristic, when there's clipping and when there's this normalization terms within the RL space, within this algorithm, it tends to shift the model's bias towards something that it already knows. It's not making the model learn something new, but since it increases the confidence, you sometimes see some accuracy gains. So the here I'm just leaving the reading list. I'll share the slides after this talk. But most of these works, what they basically say is that so you have four quadrants here. Basically, you have high probability tokens, and you have positive samples, you have negative samples, and low probability tokens. So what most of these works in this slide basically say is that what RLVR does, is it basically collapses the entropy within a model. And what is when there's a collapse in entropy, what it does is it's not really allowing the model to explore more solutions. So all of these approaches that have come out in like answer in as follow-ups to this major RLVR work is basically saying there's an entropy collapse. So maybe we should do something that increases this entropy. Maybe we can suppress these low probability tokens or high probability tokens, which are key to this exploration phase. And that is what most of these approaches that have come after have been about. So this was mostly me talking about the algorithm that we mostly use for this setup that we mostly use for training these models, which are LVR. The takeaway mostly being that given what we know right now, we don't really know if there's pure genuine exploration, and at the same time it's very hard to do that because of one, annotation, and two, there is no ground truth or like exploration spaces. So ideally what you would want to do when you're doing something like this is you would take some model and you would see everything that it can explore right now, and you would train it with RL and then see if it's doing some genuine exploration after. But one, you would need a lot of annotation power to see if it's doing genuine exploration or not, and that is really really difficult. But within the confines of our reasoning setup, there might be some deficits when we just do RLBR. So okay, now coming to the meat of the stock mostly is that studying failure in reasoning models is done in two styles. One is using the algorithm on synthetic tasks. What you're basically doing in this case is uh, so you cannot really when you are really evaluating a model on something and you are saying that okay, this is because of the reasoning part. You cannot really disentangle the if it's because of retraining, is it because of long context, is it because of some other attribute within the model training setup, and what these approaches where they show failures in reasoning models. The first approach, the using the algorithm, is basically they are using RL to train a model on synthetic tasks and seeing if it works or not. The second approach mostly is basically using current generation LRMs, which is large reasoning models, and then evaluating them on different kinds of tasks and seeing if they do well or not, or at least showing that when a well enough benchmark is made to show a specific deficit, you can actually show some interesting conclusions from these models. All right. Almost everyone might be familiar with this paper, which came out this year, which is Illusions of Thinking, Understanding the Strengths and Limitations of Reasoning Models. The long and short of this paper mostly is that in this paper, what they say is that although the model is the base model, is showing like gains when it comes to like the stars, math 500, AME 24, and AME 25. But when you look at the reasoning models gain, it's sort of inconsistent among the models. And we don't really know if reasoning was as good as it says, it should have had consistent gains across these tasks. And that is not really the case. So the way they do this, so what they do instead in this paper is they have these four toy tasks, which is Tower of Hanoi, checkers, jumping, river crossing, and blocks world. And what they are doing is they ask a model, like given these four puzzle environments, they're asking the model to basically start solving these various tasks, like in this confine of like this environment space. This is what it basically looks like. Like you have this LLM response, wherein you are given a prompt, and the LLM, like in this thinking brackets, is giving all the moves, and you have this final answer. And what they do in this paper is they extract all these moves from the thoughts and they extract the final answer as well. And what this helps them do is not only evaluate into like the final stage, they can evaluate intermediate stages as well. What this paper says is as the complexity of the task increases, uh, most models collapse and they cannot really solve complex tasks. And while when it's like low complexity, both reasoning models and non-reasoning models are the same. They can do it perfectly well. When it's medium complexity, non-thinking models are much worse than thinking models. But when it's high complexity, neither of these models can do well. And they show these are across these four environments. As you can see, across the four environments, you see a very similar trend. Wherein low complexity, it always works out, but as the complexity of the environment increases, it can't really do a good job at solving these tasks. One interesting thing that they show in this paper is even if the model is given the execution algorithm, like even if it's given the algorithm to solve the problem, it seems that the model can't really execute well. And that is an open question that they end with in this paper, which is really interesting because you would think that the discovery of the solution is the most important or like most difficult phase. And if it knew that, it would be able to solve these problems. But that's not really the case here. Even like when they try giving the model an algorithm to solve these, it can't really do that as the complexity increases. Uh, a parallel paper which sort of came out from Google at the same point is this task. Like frontier LLMs still struggle with simple reasoning tasks. What they are doing in this paper is if you have an original puzzle, which is a very simple thing, like given in this original puzzle, as you can see, 13 purple, 15 yellow, and 17 maroon chameleons are found on an island. When two different colored meet in a pair, is it possible all the chameleons are the same color? What they do in this unpuzzle is basically they are perturbing the original question to slightly differently, and the answer changes as well. And then they have this context shifted unpuzzle as well. So they are basically perturbing these questions that they have in slightly different ways. And they have different kinds of tasks here, which is basically word counting. I'll quickly go back to the slide. They have logic evaluation, they have logic negation, and they have one more task. And what they are doing in this is first, what they establish is that as the complexity of the task increases, the accuracy of models goes down. In this word counting, basically, what's asked is given a text paragraph, count the occurrences of every word in a K long list. M is the paragraph size. K is the number of words that it has to count. When it's like when you just have to count one word, even if the paragraph size is high, these models can do a pretty good job. It's O1, 4.0, R1, uh, and then you have Claude 3.7, Gemini 2.0 Flash, and Gemini. Yeah. In this, what they show is that when it's low, it can do pretty well, but as the complexity increases, models start getting worse and worse. And even though O1 does pretty well at this size, they say that when K is greater than 3 and M is greater than 2000, even O1 collapses to like sub 40%. Now, this is only constructing the task. You have not really added the unpuzzle part or the context shifting yet. And they have these other tasks. And the general trend is same, is as the complexity of the task increases, these like their accuracy goes down, ultimately proving that what they want to prove with this is that generalization is basic length generalization is basically when you're training a model on low complexity tasks or showing you complexity tasks, you want the model to generalize to a higher space as well. That's true generalization. And what they're showing with this is basically all the model can solve the lower complexity space as well. It's not really generalizing to other higher spaces. So this is the like so these are the numbers when there is like unpuzzled. So unpuzzled is the benchmark that they came out with. So even when they give the models like normal puzzles, they have got like good accuracy, about 80% across the board. But as soon as they start changing like puzzling, like unpuzzling it, basically changing the context, like adding subtle perturbations and changing the way the model interprets it, they see that like accuracy drops across the board. And there's like different types of these things. uh, One of the things that you'll see is that it's sometimes incorrect with delirium. Like it's like as you can see sometimes if when you're using these models, you ask it a question and it's incorrect, but it just doubles down on it instead of saying that it's wrong. So that is entirely missing. uh, this paper is not really about a reasoning failure, but I've just added this here to showcase something which I like the open question in this paper, this earlier paper, which was basically models cannot really execute well. So this paper studies that for agentic tasks. And what that looks like basically is in long horizon tasks, when you're doing it in an agentic manner, you first want the model to plan, and then you want the model to execute. And then in agentic tasks, you have an environment. So whenever you're executing something, the output will change. And basically, you want the model to execute. In this paper, The framework is basically they are giving the entire plan to the model and they are asking the model just to execute it. They are not asking the model to do anything else. And like so basically planning is you're asking the model like what steps should I take. Execution is you just need to carry out the steps. Knowledge is you need to be informed about the different steps. A reasoning task is planning the steps to solve some task. Agentic is you need to plan the actions, take feedback from the environment, and keep executing them one after the other. What they find in this paper is that as model sizes grow, they do pretty well on like the way they can solve tasks increases, the long horizon execution ability increases, and thinking models do better than non-thinking models. But at the same time, one interesting that they found both in reasoning models and non-reasoning models are larger, like they are prone to self-conditioning. Is basically if they've made an error earlier in their plan, or like if given a plan, if they've made earlier in their execution, that just compounds more and more down the road, and like it just blows up, and that is where they collapse. They're not really aware of this, and they cannot really recover from this fault in their execution. So this paper is mostly about this kind of mostly about the fact that long horizon execution is something models still fail at. You could look at it at two ways: is basically they are not aware of their own context, or you could say maybe the context length is not enough, and that is why they have to use some other heuristics like compressing the context and other stuff like that. But yeah, something interesting to think about. Right. Now coming to tasks mostly. So these are like benchmarks which were found to like throw models off in various kinds of performance. The first one is recitation over reasoning. How cutting edge large language models can fail on. Sorry. Yeah. So in this paper, what they do is given elementary tasks that a model can actually solve. The elementary task is very simple here. A boat sails at 15 kilometer per hour, and it's giving some context here. How long does it take to return from B to A? And there's a very simple like formula for that. What they basically do in the subtly changed condition is that they're just changing traveling from floating this introducing these small perturbations. And what they find is that most models do much worse on these like small changes. One thing to keep in mind about this specific benchmark is that this was Chinese only, and maybe that is why you could say that these elementary questions early on had a template in the model's memory, and that is why they could solve it. But as soon as the template shifts, they are not able to generalize to a slightly different version. That could be the case, but at the same time, something like these are of the same level. It's not like it's something much complicated. They keep the level. More often than not, what they've said in the paper is they've made the perturbed question even simpler than the original question that the model could solve. And even then, these models ultimately fail on these tasks. Yeah, as you can see, generally, in this case, on modified tasks, the accuracy on these models is much lower. Uh, and the Chinese models don't show that level of uh, like loss of performance, but they even then they show some loss in performance. The next benchmark is basically missing premise exacerbates overthinking. In this, what they basically do is in non-reasoning models, a good feature is when you are giving a question like what is the value of A, the model will just say, okay, we are just starting the conversation. You have to provide some context. But in reasoning models, when you ask it a question like that, it's just doing a lot of overthinking, and we've not even given it any context, and it's just starting to like think. And like when you frame it in a question form, like James decide to run 3 sprints 3 times a week, he runs 60 meters each sprint. there's a straightforward answer for that. Like it can just calculate. But when you remove some context from the question, it just keeps on thinking instead of saying like, okay, there is some missing premise and you need to fill it in. And that is the way they have framed this entire like these are the four kinds of tasks that they look at. You have MIP formula, MIP swamp, MIP GSM8K, and MIP math. And basically these are the methods that they've done to have these missing premise. There's a rule-based generation for the formula. For GSM8K, they've just removed some premise because these are elementary questions. And for MIP math, something similar where they've removed the premise. So what this graph basically says is the green line is uh, like accuracy rate when the question is well defined. The red line is basically the accuracy rate of abstaining. Like basically the model should identify and say, okay, something is missing in the premise. And the bars that you see are like the token response length. And for well-defined question, it's blue bar, and all the orange one is for like in missing in premise. What they find in this paper is when a question is well defined, reasoning models are generally much better than non-reasoning models, without a doubt. But even then, they generate a lot more tokens than non-reasoning models. What when there is something missing in premise, non-reasoning models can do a quick, like they do a much better job at abstaining compared to reasoning models. And that's generally the case. Like you might say that, okay, that is not the case in GPT-o1, but across all these other models, that is definitely the case. And not only are they much worse at these types of questions, they also generate a lot more tokens, showing that they are just thinking without any end to it. And that is like a reasoning failure. Is why is this shift happening? And that is something to think about. In abstention bench, so in this paper, what they're basically doing is they have these six different types of unanswerable questions, and the unanswerable questions fall in these six buckets, wherein you either have underspecified context, the answer is actually unknown, more context will not make it known, either it's subjective for those kinds of tasks. The answer is not really correct or wrong. It's stale data. You're asking it something about who's the president, but the model cutoff is 2024, and either it could be stale data in the form of a question. The premise is false, and there's like underspecified intent. And what you want the model to say ideally is it should say like abstention response is something different. What they find is basically when like sorry, one sec. Yeah, when it's stale and oh, when the answer is unknown, the abstention recall is basically whenever the model should abstain from actually answering, and it's actually abstaining. That is the recall that they're measuring. When the context is underspecified, when there's a false premise, and when it's subjective, models usually fail. But for these other kinds of like tasks that they found in this broader benchmark, they find that models are usually good at some of these tasks. But when it's these underspecified context or understanding the premise of the question, they can't really abstain and they just go on. They are not really aware of their own like these limiting factors. Abscess bench is something very similar to missing in premise. In this benchmark, this is basically an extension of needle in a haystack. In needle in a haystack, basically you're just asking the model to either fill in the blank, or you're asking the model to find something or a very specific thing. In abscess bench, something is omitted from the context, and the model is asked what is omitted in the modified context, or it's even asked, is there something omitted? And they do it for four different kinds of domains. One is poetry, the other is numerical, and then they do it for GitHub PRs as well. And finally, absence token is when they actually like they just omitted, but they are writing that there's some missing line. So what they find is that models like Gemini Flash, these larger models are generally better at poetry. You could say that as the models are much bigger, poetry is something they're really familiar with, and that's really in their memory. So when something is missing, they can identify it. And at the same time, for numerical series as well, that's a similar case. But for GitHub PRs, when something is omitted, they can't really identify that some context is missing. uh, what they find is whenever they have this absence token, this missing line, the model performance increases up to about 40%, which is not really something like it's not surprising because at that point, this just becomes a needle in a haystack problem because you're just asking the model is something missing or not and can just read that token. One other paper that came out this year is this feedback fiction. What this paper basically does is given like when it starts from so this is what the setup looks like. You are given a solver LLM and it's like given a question, there's a model response, and what it does if the answer is incorrect, there is a generator LLM, which is much more powerful than your solver LLM, and it's giving some correct feedback. And you're basically asking the solver LLM to incorporate this feedback because over time, in the case of humans, if you're told what is wrong, you can usually recover from your errors and you can incorporate that. And ideally, what you want is that the model just learns from this and gets better. What they find, so what does this graph, right? This graph is basically the number of iterations of feedback, and the dotted line that you see is the like the bar you expect. Like over time, you want the model. Ideally, what you would want is that as the number of times the feedback is given to a model, it just keeps getting better and better. Okay, so what they find in this paper is that even like at some point, at some level of feedback, the model just plateaus and it does not really get better over time, even though it's given feedback that something is wrong and you need to consider this. That is this is by stronger LLM, and this happens across stuff like AIME, Privia QA, GPQA, and MMLU Pro. And like even though there's like 10 iterations of feedback, it just plateaus and it cannot do it any longer. There's two ways to look at this, right? Either the feedback quality is wrong, or there is like it's not really understanding the feedback, or there's some feedback like resistance, and they term this like that is the major failure mode of these models if they can't really incorporate feedback. And at the same time, some people might say maybe this is a problem of long context, and if there was more context, maybe the model could do a better job of this, incorporating this feedback. And just adding these small notes here and there in these papers to just keep in mind that they were constructed in a certain way, and maybe you can explain them with some deficits in this model, and that's not a failure in reasoning itself. But today, given what's available, this is how we should think of it. Yeah, and what basically the conclusion of the paper is that feedback resistance is that this inability to incorporate feedback is what is really the failure mode. One of the last papers that I'll be covering in this, which is not really a failure mode in reasoning per se, but something very interesting to look at is that too good to be bad on the failures of LLMs to be role playing villains is basically looking at all kinds of models in reasoning models and non reasoning models. Something you ultimately do when you train models today, open, closed, or source, like open source or closed source, is basically you have this safety training and you have all kinds of training in there. You are training it to be good, nice, and all of that. And what this paper is basically doing is they have this role playing benchmark, and there are four levels to it. You ask the model, you're giving a model a prompt to role play a specific character. It's either a paragon of virtue, a slightly flawed character, an egoist, or a villain. So these are the four levels. What they find is models are generally very good at role playing like these paragons of virtue or slightly flawed characters. But as soon as you go to something negative, like egoists or villains, models are much worse at playing these kinds of characters. And something to think about here is that since a model is already trained on certain kinds of safety protocols, they cannot really break out into a different kind of role play or this kind of like prompt structure that they've ultimately given for these different kinds of villains. And these are the different like moral role play benchmark that they have. These are the different kinds of like they have candidate traits, and there are about 77. These are the top 20. It's loyal, kind, which is simple, and then to manipulative, arrogant, and cautious. What they basically find is this is what the character profile looks like. You have these character names, and you're just giving it the traits that it should actually embody. And what they find is that when it goes to villainous roles, models can't really do that, and they are very, very bad. And on average, even though they are good at flawed and paragons of virtue, they are much worse at villains and egoistic characters. Okay, so I'll wrap up the talk now. Since we are coming like on the hour mark, I don't want to take up too much time. But this benchmark, to give you a very short idea about this benchmark, is basically it's inverse instruction following. Instead of asking the model to do something, you're asking the model to not do something. Is you must strictly avoid using bullet points format. And what they find is that models are generally bad at avoiding things instead of following a specific instruction following criteria. And they do it in both in Chinese and in English. And I actually wanted to go through the entire data construction process because ultimately in designing benchmarks, this is always a good takeaway to look at how it was created if ever you want to do it yourself. And these are the kinds of instructions that like the model is given. Is either there's some question correction, there's like code without comments, there's intentional textual flaws, or there's some instruction modification. And what they find is that across these different kinds of errors, models are generally worse. I mean, you might say that 70% is good enough, but when a model is getting 100% on instruction following, it's surprising that it's not getting as much on inverse instruction following. That is a point. Uh, I'll skip this work. Uh, this paper is, I know I've gone through a lot of papers and this is probably hard to follow right now, but this paper just came out like last week. And what they do in this work is reasoning bench, and they are trying to measure the instability of LLM reasoning. One thing, if you've ever read an agentic benchmark paper in the last year, you must have seen two types of evaluation. One, they do pass at K, and the other, they do pass raise to K. What pass at K is basically you're just asking the model to like solve it multiple times, and if one of them is right, you're rewarding the model. Pass raise to K is basically you're asking the model to do a task again and again and again, and seeing the number of times it's actually solving the task. Pass raise to K is basically a reliability measure, and that is what you want from your agents. You basically want your model to always do the right thing when it's an agentic task and the right way, and you don't want it to stumble. What this paper basically is evaluating in reasoning is given a specific query and they are just sampling the model again and again. What they find is that one, they generate different strategies, and two, they just generate different answers. And there's a lot of instability in the way they do this. You can attribute this to many things, that these are non-deterministic models, but this is something expected from a reasoning model, that it would always converge to a very similar aspect. And this is the scaffold that they use. You have an agent, a model which is coming from an API, you have a state and environment, and you have these different kinds of methods. What they find, like these are the different kinds of methods that they have. You have, so these are all methods for reasoning. You have this chain of thought, you have self consistency. React is a framework, agentic framework. Fleet of agents is a framework wherein you are asking the model to evolve. Like when you have an meta prompt model which is looking at the task and evolving the prompt as well. What they find in this is that uh, the evolutionary setup that they have, a reasoning strategy is generally better. But across the board, across all these different kinds of reasoning strategies, there's a lot of variance, and that is definitely something that needs to be avoided. And that is not just the case for reasoning methods, but it's also the case for reasoning models. And there's a lot of variance in this. Like, so what they trying to showcase in this paper is there's a lot of instability in the reasoning, and there's no consistency in a way a model thinks. Some last thoughts that I just wanted to leave you with is where might these errors stem from? One thing to look at is there was this paper, reasoning on memorization. In this, they take a Quen 2.5B model and they are giving 60% of the question, and they ask the model to complete the question. And what they find is that Quen 2.5 Math 7B can complete the remaining 40% about half the time. What this basically says is maybe the model or like this data set really appears in the training set. And what this means is that, well, it's contaminated and we are now seeing that these are reasoning models. It's impressive, but at the same time, when you're giving it 60% of the question, it's actually like accurate. It's an exact match. It's not an approximation. They find that half the time it can entirely generate the rest of the question as well. And one last thing that I can't go too deep into, but I've left some links in the paper, like in the slides, is reward hacking. One of the biggest things in RL that not really looked at today because it's very hard to measure is this thing of reward hacking, wherein you like when you train a model too long in RL, it'll find some loopholes in the environment and it'll just start exploiting those. So one of the easiest things to do, like one of the easiest places to measure this is in code tasks, because how do you reward a code task, right? When you're training an RL model, is you are rewarding it and the amount of test cases passed. So what they do is if the test cases are available to the model, it will just modify the test case to say always true or something like that, and it's just going to hack the test case instead of actually solving what it set out to. What this paper does is it mutates SWE bench to obtain impossible bench. And they have these assertion tasks. Basically, they have these test cases. And if any of these test cases pass, it means that the model actually cheated. And they do this to accurately assess and study test case exploitation. Lower is better. What they find is GPT-5, Sonnet 3.7, Opus 4.1 are like exploiting these test cases. And that's something to keep in mind, right? When you're actually using these models to develop something, you might have seen sometimes whenever there are some test cases written, it's always just going to the test case and saying, okay, this test case passed. But when you actually look at the code, it's not really solved anything. So this is like trying to look at those kinds of cheating. And this was a benchmark developed with that in mind. And reward hacking is something that is found across different kinds of tasks. If you look at the DeepSeek Prover V2 paper, in the original version, they claim an extraordinary ability that the 7D model can solve a few problems. But when it was actually released, members in the community looked at the problems and saw that it was actually exploiting a specific aspect in the lean language. And that has since been fixed. And in the version 2 of the paper, you can see that they actually mentioned that it was a reward hack. Uh, Going like in more into the paper, it's basically you have these impossible test mutations. It should be impossible to actually pass these test cases. But since it's in context, the model can look at these test cases. It's just going to write some code, or like it's just going to manipulate these to actually pass. What they find is that models are like generally they definitely do this, and this is one example of designing a benchmark to actually see if your model is reward hacking or it's actually solving your task or not. So that's actually it on my end. Sorry for the long talk. And I've added some papers in the appendix for like these are non-verifiable tasks, some for writing and some for emotional verification, some mostly on actual evaluation of large language models, reasoning models, and the pitfalls, and some more papers on reward hacking and whatnot. So thanks a lot for calling me for this talk. And yeah, if there's any questions, happy to answer them. I know I went through a lot of papers, but at the same time, I wanted to give you a broader perspective instead of like, yeah, just a single paper.
Thanks, Pawan. Thank you so much for the super enlightening talk. Yeah, lots of stuff here, but a really nice overview. Um, I guess I'll just kick it off with one question. In that some of these failure cases, I definitely agree with you, are reasoning failure cases. Uh, of course, some of the papers you shared have since been criticized, like the illusion of thinking. Um, but I also feel like other papers, it's harder for me to say, like, agree that these are reasoning failures. For example, um, you know, following not instructions, like the inverse instruction following.
Yeah.
That to me feels just like more like an RLHF like the models have to be continued to be post trained to like pay attention to negations, right? Um, like it's a little unclear to me like that actually it's a reasoning failure. So I wonder like how you think about this split here. Like what makes a reasoning failure specifically a reasoning failure?
Yeah, actually, I definitely agree on that. Inverse IF is that that paper. I did not really select it as to show the reasoning failure. It was, as you said, uh, these failures depend on what we focus on and what benchmarks we hill climb. We are now hill climbing, like since you want to hill climb this IF eval and multi IF eval, you're just basically giving the model a lot of instructions and you're asking the model to follow it. So that's the kind of data that appears in its post training setup. But if we were interested in this inverse IF eval, maybe that would appear and it would then become a benchmark we would hill climb on. So sometimes the things that we see as deficits are not really deficits in a way of the reasoning, but it's just that something we are not focused on. So the model is just performing poorly. And yeah, I definitely agree on that front. It's I just showed this to say that specific point is that we are not hill climbing on this, and that is why we don't see good performance on this. And it could be seen as a reasoning failure at the same time. You're asking the model to simply adhere to a specific instruction, and it's just a negative instruction instead of a positive one. So you should see some performance at least. But yeah, I agree on that front. It's just something that we are avoiding, and it is easily fixable with the right data.
Thank you so much, Pawan. Yeah, so if anyone else has questions, please raise your hand.
Uh, Excuse me. Hello.
Yes, we can hear you.
Yeah. There was a discussion about that RLVR will be also helps in the creativity as a source of engagement and all those things. And when we defined a well good well good question such that it can also perform in the other domains creatively, as for an example creativity, but the understanding and the reasoning steps that has been taken in the model that it has been explored is lot different with the uh, reasoning steps that it can take in another domain, right? So how the reasoning strategies does really help in terms of the long context. If we give long form question which is well defined, how it helps in achieving the reasoning? Is there any works that has been researched so far?
Are you basically asking if there is transfer when you train it on a specific domain to other domains?
Yes, with the well-defined long form functional prompt question, and the instructions are also not multiple Fs. Yeah, but the context is more,
Uh,
and
actually,
the context from the uh, in the instructions does have a 60% uh, things, and it has to achieve a good reasoning and predict some creativity in terms of text generation.
uh, I think like answering a part of your question definitely is that there has been work which shows transfer from one domain to other. If I was giving a math talk today, I would have shown that paper. Basically, the math reasoning is very, very popular. If there has been work which shows transfer for when models are trained on mathematical tasks, it actually shows overall gain across different kinds of domain. And this is not just for like elementary problems, right? When you try to solve for math, if you actually look at the length of COT that these models generate, it's in tens of thousands of tokens. But when you just do like train it for math alone, you're not training it for anything else. There's actually gains for all other different kinds of tasks that that there exists. I'll try to include that paper in this talk or like cover it in one of my future talks, definitely. Yeah, if there's like if I did not get your question well, just DM it to me or on the Discord channel and respond there. Yeah, go ahead, Luigi.
Can I see the paper that you are referring as like if
Yeah, I
you
will
can?
send that to you. Yeah, okay.
Okay, thank you.
Yeah, I was wondering, am I? Can you hear me?
Yeah, I can hear you.
Oh, excellent. I was wondering something about visual reasoning examples because I often, miss them from a lot of these papers that I look through. Because one thing I keep testing on a lot of multimodal LLMs is trying to generate an SVG code of an image, right? So that's, in my opinion, a very good use case to combine a code generation with visual reasoning. Because what always seems to happen is you generate an SVG code and it doesn't match the image you input. Even if you help a model by prompting very exactly what is displayed on the image. And I'm talking about a very simplified image here, like suppose you have like a structure of 4 squares and 6 lines, all 90 degrees separated from each other, right? You will see that they always mess up. And what makes this interesting for RL and feedback is that if you have a VLM, you can output the resulting SVG image, render it, and give it back and state, look, this is the result. Please fix it, or be more specific, if you use human feedback and point out what the problem is. And then you will see it will once again fail, and it will fail and fail and fail and fail and fail. Every model does this at the moment. The only model that comes kind of close is Gemini 3. I was just wondering if this is something you have come across in the literature yet, because it seems to be a very interesting eval that combines code generation, because you can one hand reason over if the SVG code is generated correctly without flaws, and then you can render the SVG code and then give it back to the VLM to see from, look, this is what you're supposed to be recreating, and this is what you recreated. And then in the thinking tokens, you can see that it often will reason, oh yes, I can totally see these lines are not symmetrical, or this shape is wrong. Or often it will miss it. But yeah, it's
Yeah,
perhaps a little bit harder to RL because it also depends on whatever tokenizer is used for the visual component of the VLM. It's a bit
I
convoluted. I hope you understand what I'm talking about.
yeah, I did. So one sec, I will just. So I know of this SVG bench which is on GitHub. I will share that on the
Oh no,
Discord channel.
I know that
Uh,
one. I know that one. But that's explicitly what I mean is you input a photo, so like a photograph of a sketch of something. So you take some graph paper, pencil, you make the shapes. So deliberately not basing it on a digital one, and then you ask the model generate lines from this.
Oh yeah, that eval does not exist. I follow most of the benchmarking space. Yeah, being honest here, that I don't follow as much in the vision benchmarking, but since there's a lot of overlap in code, yeah, from what I remember, there is no specific eval that covers this specific setup that you just described.
No, yeah. The SVG bench, I did look into that, but I was a bit disappointed because it was still very
Yeah, it's very simple. Yeah.
yeah, and still it's missing that key component because the what was that paper you just linked about the feedback? I almost copied it. It was
Feedback
about
friction.
yes, exactly.
Feedback friction. Yeah.
You clearly see feedback friction in that example, which makes it interesting to look into. I do think that it has very I think like that those kind of problems are perhaps interesting to solve with actually smaller reasoning models. And these kinds of models probably also have more industrial use cases. You know, generating vector-based code from real images, because all of the generative graphs we have currently are often yeah, pixel-based, which is often inflexible.
Yeah, I generally agree that we are still, I think mostly for benchmarks, I'd say that we are still in the simple reasoning problem domain, and that is why we have not like chosen to have these more complex tasks. But I expect like next year to be filled with a lot of like more interesting benchmarks, which maybe will not be solved by general models, but we'll need more specific models to solve these more interesting use cases.
Yeah, I'm looking forward to it. If I had to compute, I train something small because I genuinely think that yeah, because it's so much is in the specific thing that I'm describing is visual based, right? It's basically combining shapes. You do need code generation and reasoning that you could, you know, basically generate a very small model, something close to what ArcAGI does with the bespoke models. But yeah, I'll refrain from elaborating now.
Yeah. Thank you.
Thank you, Pawan. This was great. And thank you for answering all the questions.
Thanks a lot.